Welcome back to Whispering Universes, where we explore the grandest questions about our cosmos and the quiet mysteries that await us across the vast expanses of time. Tonight, we embark on a journey unlike any other, a voyage not through space but through time, stretching forward across billions, trillions, and eventually incomprehensible eons into a future so distant that the very concept of years loses meaning. We're going to explore what happens after the last star dies, after the final glimmer of starlight fades from the universe, leaving behind a darkness more complete than anything you can imagine. This isn't a journey into despair or cosmic horror. Rather, it's an exploration of transformation, of the universe's patient march toward its final chapters, and perhaps most importantly, a meditation on what these distant futures reveal about our own precious moment in cosmic time. You exist, reading these words or listening to this voice, in what cosmologists call the stelliferous era, the age of stars, a period of cosmic history that, while lasting trillions of years, represents merely a brief flicker in the infinite expanse of time, stretching before and after. Understanding what comes after helps us appreciate what we have now. The universe began approximately 13.8 billion years ago, in the event we call the Big Bang, an expansion of space itself that continues to this day. In those first few 100 million years, the universe was dark, filled with cooling hydrogen and helium, but no stars to light the void. Then gravity began pulling matter together, creating the first stars, massive blue giants that lived fast and died young in supernova explosions that seeded the cosmos with heavier elements. Generation after generation of stars has followed, each creating planets, systems, and in at least one case, life capable of contemplating its own origins. But star formation cannot continue forever. Stars require raw materials, primarily hydrogen gas, and that gas exists in finite quantities. Over time, more and more of it gets locked inside stars, burned into helium and heavier elements, or dispersed into space where the expanding universe carries it beyond the reach of gravity. The rate of new star formation peaked approximately 10 billion years ago, and has been declining ever since. Our own sun formed relatively recently, about 4.6 billion years ago, when the universe was already past its prime star-making years. Looking forward, we can calculate with reasonable precision when the last star will form and how long that final star will shine. We can map out the sequence of events that follows, each phase lasting longer than the last, each one stranger and quieter than the phase before. The mathematics of thermodynamics, gravity, and quantum mechanics gives us a roadmap through the unimaginable expanses of time, showing us what persists, what fades, and what transformations await matter and energy in the far, far future. Why does this matter to you, here and now, in a universe still filled with brilliant stars? Because understanding the full life cycle of the cosmos, from its fiery birth to its cold end, places your own existence in profound context. You live in the golden age of the universe, when stars still burn bright, when galaxies still spiral in majestic formations, when energy gradients allow for complexity and life. This epoch won't last forever, but knowing that makes it more precious, not less. The stars above you tonight are temporary, and that temporariness is part of their beauty. As we journey together through these future eons, I invite you to let your mind expand to embrace timescales that dwarf human history, the way human history dwarfs a single heartbeat. Let the vast stretches of time wash over you gently, without urgency or anxiety. We're not rushing toward an ending, but contemplating transformations, watching as the universe slowly, patiently evolves through phases we can understand, even if we cannot witness them. The physics remains consistent, the laws unchanged, and through those laws we can see across billions of years as clearly as we see across billions of miles. So settle in, let your breathing slow, and prepare to witness the longest story ever told. The story of what happens when the last star dies and the universe enters its final, longest, strangest chapters. Star formation, the process by which clouds of gas collapse under their own gravity to ignite nuclear fusion, has been declining for billions of years. The peak occurred approximately 10 billion years ago, about 3 to 4 billion years after the Big Bang, when the universe was rich with dense molecular clouds and galaxies were actively colliding and merging, events that trigger bursts of star formation. Since that peak, the rate has been steadily falling, and the universe produces fewer new stars each passing billion years. The reason for this decline is straightforward. Stars form from hydrogen gas, and that gas comes in finite quantities. Once hydrogen gets incorporated into a star, it undergoes fusion, transforming into helium and, in massive stars, into carbon, oxygen, and heavier elements all the way up to iron. Some of this material gets recycled when stars die, particularly in supernova explosions that scatter enriched gas back into space. But much of it remains locked in stellar remnants like white dwarfs, neutron stars, and black holes. Additionally, the expansion of the universe continuously dilutes the remaining gas, spreading it thinner and thinner across ever larger volumes of space. By about 100 trillion years from now, give or take a few tens of trillions of years depending on specific assumptions about gas recycling and galaxy evolution, the last star will form. This final stellar birth won't be a spectacular event. It won't be a massive blue supergiant blazing with the light of 1,000,000 suns. Instead, it will almost certainly be a red dwarf, the smallest, dimmest, most modest type of star possible, barely massive enough to sustain hydrogen fusion in its core. Red dwarfs require only about 7.5% of the sun's mass to ignite, and they burn their fuel so slowly, so conservatively, that they can shine for trillions of years. Picture the scene: a small, diffuse cloud of hydrogen gas, perhaps the remnant of some ancient supernova or the last wisps of gas left in a dying galaxy, slowly collapsing under its own weak gravity. The process takes millions of years, as it always has. The cloud fragments, and the densest region at its center grows hotter as gravitational potential energy converts to thermal energy. Eventually, after patient accumulation, the core temperature reaches approximately 10 million Kelvin, the threshold where hydrogen nuclei overcome their electromagnetic repulsion and fuse together, releasing energy. A new star ignites, the last star, and begins its long, slow burn. This final star will be alone in ways difficult to comprehend. By this point, 100 trillion years in the future, most galaxies will have long since merged into single massive elliptical galaxies, or dispersed into isolated stellar remnants, drifting through intergalactic space. The sky around this last star won't show the rich tapestry of nebula and star clusters we see today. Instead, it will see mostly darkness punctuated by the dim, fading embers of ancient white dwarfs and the occasional dead neutron star. Galaxies beyond its own will have receded beyond the cosmic horizon, carried away by the universe's accelerating expansion, their light redshifted into invisibility. The molecular clouds that birthed earlier generations of stars will have long since dispersed. Star formation requires not just hydrogen, but also dust grains that help cool the gas, allowing it to collapse more efficiently. These dust grains come from earlier stellar generations that created heavy elements and expelled them in stellar winds and supernova. By the time the last star forms, even this dust will be rare, scattered thinly or locked inside dead stellar cores. The conditions for star formation will have degraded to the bare minimum necessary, just barely sufficient for one final ignition. After this last star forms, no more will follow. The remaining hydrogen will be too diffuse, too scattered across the expanding universe to ever collect again in sufficient quantities. Gravity's patient pull, which has been gathering matter into stars for hundreds of trillions of years, will finally lose its battle against cosmic expansion and entropy. The universe will have used up its fuel for making new stars, and the stelliferous era, the age when stars dominate the cosmos, will begin its final countdown, ticking away the lifetime of that last red dwarf. This last star will burn for trillions of years, longer than all of recorded human history, by factors too large to comprehend easily. But even it must eventually exhaust its fuel, fuse its last hydrogen nuclei into helium, and fade from the sky. When it does, when its fusion reactions finally cease and its light dims for the last time, the universe will enter permanent darkness, never again to be illuminated by the natural light of a star. Everything that follows will unfold in cold and shadow. Long before that final star forms, red dwarfs will have already become the dominant stellar population. These smallest of stars, ranging from about 7.5% to 50% of the Sun's mass, vastly outnumber all other types. They constitute roughly 70% to 80% of all stars in the universe, yet they're so dim that not a single one is visible to the naked eye from Earth. Proxima Centauri, the closest star to our solar system at just 4.2 light-years away, is a red dwarf, and even it requires a telescope to see. Red dwarfs survive through extreme efficiency. Unlike the Sun, which has a radiative core where energy transfers outward primarily through photons bouncing randomly through dense plasma, red dwarfs are fully convective. Convection currents circulate material from the core to the surface and back again, like water boiling in a pot, but on stellar scales. This convection means the entire star participates in fusion, not just the core. Fresh hydrogen continuously cycles into the fusion region, while helium gets transported outward, preventing the buildup of inert helium ash that eventually chokes off fusion in larger stars. This complete mixing gives red dwarfs extraordinary lifespans. The Sun will exhaust its core hydrogen in about 10 billion years total, having already burned for 4.6 billion. A red dwarf with just 10% of the Sun's mass will burn for 10 trillion years or more. The smallest red dwarfs, those barely massive enough to fuse hydrogen at all, might last 20 trillion years. To put this in perspective, the current age of the universe, 13.8 billion years, represents less than 1,000th of 1% of a small red dwarf's lifetime. These stars are so long-lived that not a single red dwarf that has ever formed has yet reached the end of its natural life. Every red dwarf born since the Big Bang is still shining. As larger stars die off over the next trillion years, red dwarfs will remain, gradually coming to dominate the visible universe. The Sun will swell into a red giant in about 5 billion years, eventually shedding its outer layers and leaving behind a white dwarf. Within 100 billion years, all Sun-like stars will have met similar fates. Within a trillion years, even the longest-lived larger stars will have exhausted their fuel. But red dwarfs will continue burning, patient embers in an increasingly dark cosmos. Eventually, even red dwarfs exhaust their hydrogen. When they do, something remarkable happens, something no one has yet witnessed because it takes far longer than the current age of the universe. Theory predicts that a red dwarf, having consumed all its hydrogen, will transition into what's called a blue dwarf phase. The star contracts slightly, heats up, and actually becomes bluer and slightly brighter for a period before final extinction. This seems counterintuitive, a dying star growing brighter. But it follows from the physics of stellar structure and the star's gradual contraction as fusion ceases. The blue dwarf phase won't last long compared to the red dwarf phase that preceded it, perhaps a few 100 billion years at most. Eventually, the star can contract no further without collapsing completely, and lacking the mass to ignite helium fusion or any subsequent fusion process, it simply cools. The nuclear reactions stop. The star becomes a helium white dwarf, a dense, Earth-sized ember slowly radiating away its stored heat into space. These helium white dwarfs differ from the carbon-oxygen white dwarfs left by Sun-like stars, being composed primarily of helium, since red dwarfs never got hot enough to fuse helium into heavier elements. Imagine the universe 20 trillion years from now. Almost no new stars form. The massive stars are long gone, having exploded as supernovae or collapsed into black holes billions of years ago. Sun-like stars have all died, leaving white dwarfs behind. But red dwarfs still shine, countless trillions of them scattered through space, providing the only natural light remaining. Galaxies have merged and dispersed, but wherever you find matter still bound by gravity, you find red dwarfs, loyal candles burning in the cosmic night. These red dwarfs will be the universe's last witnesses to stellar processes, the final inheritors of a cosmos that once blazed with blue giants and supermassive stars. They carry forward the legacy of nuclear fusion, the alchemical process that transforms simple hydrogen into more complex elements and releases the energy that makes stars shine. For tens of trillions of years, they alone will keep that ancient fire burning, a bridge between the bright youth of the universe and the cold darkness that will eventually claim everything. When the last red dwarf finally exhausts its fuel and fades, when the universe's final blue dwarf cools into a white dwarf and begins its own trillion-year journey toward absolute zero, the stelliferous era officially ends. From that point forward, no natural process will create light through fusion. The universe will never again witness the birth of a star. The age of stellar fire, which began merely hundreds of millions of years after the Big Bang and lasted for hundreds of trillions of years, will give way to the degenerate era, a time dominated not by shining stars, but by their dark, cold corpses. White dwarfs represent one of the most common final states for stars, the end point for anything between about half the Sun's mass and 8 times the Sun's mass. When these stars exhaust their fuel, they shed their outer layers as planetary nebulae, those beautiful shells of glowing gas you see in astronomical photographs, and leave behind their cores, dense spheres supported not by fusion or thermal pressure, but by quantum mechanical effects, specifically electron degeneracy pressure. A white dwarf packs roughly half the Sun's mass into a volume about the size of Earth. This creates densities approaching 1 million times that of water, meaning a teaspoon of white dwarf material would weigh about 5 tons. At these densities, electrons are squeezed so close together that quantum mechanics steps in with the Pauli exclusion principle, which states that no 2 electrons can occupy the same quantum state. This creates a pressure independent of temperature, allowing the white dwarf to resist gravitational collapse, even without ongoing fusion or intense heat. When a white dwarf first forms, it's searingly hot, with surface temperatures often exceeding 100,000 Kelvin, far hotter than the Sun's surface at 5,800 Kelvin. This heat is residual, left over from the star's fusion-burning days and from the gravitational energy released during its final contraction. But without fusion to replace lost energy, the white dwarf can only cool, slowly radiating its heat into space through thermal radiation. The cooling follows well-understood physics, and we can calculate how long it takes. Initially, white dwarfs cool relatively quickly by cosmic standards. They drop from 100,000 Kelvin to around 10,000 Kelvin in the first 100 million years or so. At these temperatures, they glow blue-white, still quite bright by human standards, though nothing compared to their progenitor stars. But as temperature decreases, cooling slows down dramatically. Thermal radiation follows the Stefan Boltzmann law, which says that the power radiated scales with the fourth power of temperature. As temperature drops, the rate of energy loss drops precipitously, and the cooling process stretches out over longer and longer time scales. After about 1 billion years, a typical white dwarf has cooled to around 5,000 Kelvin, roughly the temperature of a cool red star. After 10 billion years, it might be down to 3,000 Kelvin, glowing a dull red that would be barely visible even from nearby. The current age of the universe, 13.8 billion years, means that even the oldest white dwarfs, those formed from the first generation of stars to die, have only cooled part way. They're still radiating in the infrared, still warm by astronomical standards. But give the universe time, lots of time, and white dwarfs will cool much further. After 1 trillion years, white dwarfs will have temperatures of only a few hundred Kelvin, colder than the coldest places on Earth. After 10 trillion years, they'll approach the temperature of the cosmic microwave background radiation, which itself will have cooled due to cosmic expansion to just a fraction of a Kelvin above absolute zero. At this point, white dwarfs become black dwarfs, theoretical objects that no longer radiate any significant energy, invisible even to the most sensitive infrared detectors. The term black dwarf refers to any white dwarf that has cooled to the point where it no longer emits detectable radiation. Current estimates suggest this takes approximately 10 to 20 trillion years, longer than the present age of the universe by a factor of nearly 1,000. This means black dwarfs don't yet exist anywhere in the universe. Every white dwarf currently floating through space still glows with residual heat, still slowly cooling. But eventually, inevitably, they'll all go dark. Inside a cooling white dwarf, fascinating transformations occur. At extremely low temperatures, the carbon and oxygen nuclei that make up most white dwarfs can arrange themselves into crystalline structures, essentially forming diamonds the size of planets. This crystallization releases a small amount of latent heat, temporarily slowing the cooling process. But eventually, even this heat dissipates. The result is a solid sphere of crystallized carbon and oxygen, completely inert, drifting through space at temperatures barely above absolute zero. Black dwarfs will inherit the universe for a time, vastly outnumbering the remaining neutron stars and black holes. They represent the endpoint of normal stellar evolution for the majority of stars, including our own sun. Imagine the sky of Earth 20 trillion years from now, if Earth still exists in some form. The sun will be gone, replaced by a cold, dark sphere invisible against the black of space. No light, no warmth, just gravitational presence. Every sun-like star in the galaxy will have met the same fate, leaving behind a vast population of black dwarfs, cosmic tombstones marking where stars once shone. These black dwarfs won't remain entirely unchanged. Over incomprehensibly long timescales, quantum tunneling and other exotic processes might alter their structure. Proton decay, if it occurs, will eventually cause even black dwarfs to evaporate into radiation. But these processes operate on timescales of 10 to some 34 years or more, far beyond the era when white dwarfs first go dark. For many trillions of years, black dwarfs will simply drift, cold and patient, through an increasingly empty universe, monuments to the stellar age that preceded them. Neutron stars represent another endpoint of stellar evolution, specifically for stars massive enough that their cores collapse beyond the white dwarf stage. When a star between roughly 8 and 20 solar masses exhausts its fusion fuel, its iron core collapses in a fraction of a second, crushing protons and electrons together to form neutrons. The result is a sphere typically around 20 kilometers in diameter, but containing 1.4 to 2 times the Sun's entire mass, creating densities so extreme that a sugar cube-sized chunk would weigh as much as Mount Everest. When first formed in the violent explosion of a supernova, neutron stars are extraordinarily hot, with interior temperatures reaching 1 trillion Kelvin or more. They're also spinning rapidly, often many times per second, due to conservation of angular momentum during their collapse. Many neutron stars possess powerful magnetic fields billions or even trillions of times stronger than Earth's magnetic field, created and amplified during the collapse process. These rapidly rotating magnetic fields create beams of radiation that sweep across space like lighthouse beams, producing the pulsing signals we detect from pulsars. But like white dwarfs, neutron stars have no ongoing energy source after their formation. They can only cool and slow down. The cooling mechanisms differ from white dwarfs because neutron stars have no ordinary matter in their interiors, only densely packed neutrons with perhaps exotic forms of matter at their cores. Heat escapes primarily through neutrino emission in the early stages, as various neutron interactions produce neutrinos that stream out of the star carrying energy. Later, as temperature drops, photon emission from the surface becomes the dominant cooling mechanism. Neutron stars cool quickly at first by cosmic standards. Within about 10,000 years, they drop from 1 trillion Kelvin to around 1 million Kelvin. After 1 million years, they might be down to 100,000 Kelvin. But like white dwarfs, the cooling rate decreases as temperature drops. Magnetic field decay also occurs, though the timescales aren't fully understood. Strong magnetic fields can persist for millions or even billions of years, gradually weakening through poorly understood processes involving the motion of charged particles in the neutron star's crust and interior. Pulsars. Those neutron stars whose rotation and magnetic alignment allow us to detect their radiation beams gradually slow their rotation as they emit electromagnetic radiation powered by their rotational energy. The Crab pulsar, created in a supernova observed in 1054 AD, rotates about 30 times per second now, but is slowing at a measurable rate, losing rotational energy continuously. Eventually, every pulsar slows to the point where it no longer produces detectable pulses, though the neutron star itself continues to exist. After billions of years, neutron stars become cool, slowly rotating, weakly magnetic objects essentially invisible except through their gravitational influence. After trillions of years, they'll have cooled to temperatures similar to the cosmic microwave background, which by that point will have cooled to nearly absolute zero due to cosmic expansion. These cold neutron stars will be completely dark, emitting essentially no radiation at any wavelength, detectable only if something happens to pass nearby and experience their intense gravitational field. Neutron stars are far less numerous than white dwarfs because they require more massive progenitors, and massive stars are rarer than low-mass stars. Current estimates suggest there might be 100 million to 1 billion neutron stars in the Milky Way galaxy, compared to potentially 10 billion white dwarfs. But neutron stars are important representatives of the extreme endpoints of stellar evolution, demonstrating how far gravity can compress normal matter before it transitions into something even more extreme. The question of whether neutron stars remain stable over cosmic timescales depends on physics we're still exploring. Neutron degeneracy pressure, analogous to electron degeneracy pressure but involving neutrons, supports the star against collapse. But neutrons, unlike protons, are unstable when isolated and decay into protons, electrons, and neutrinos with a half-life of about 10 minutes. Inside a neutron star, the extreme pressure and density stabilize neutrons, preventing this decay. However, over timescales of 10^34 years or more, if proton decay occurs as some theories predict, neutron stars might slowly evaporate into radiation. There's also speculation about neutron stars potentially converting to strange quark matter over extremely long time scales. Strange quark matter, if it exists and is stable, represents an even denser state than normal neutron star matter. A strange quark star would be supported by the degeneracy pressure of quarks rather than neutrons. Some theories suggest neutron stars might slowly convert to this state through quantum tunneling processes, though the timescales involved would be astronomical even by cosmological standards. For our purposes, contemplating the far future, neutron stars fade into the background along with white dwarfs and black dwarfs, becoming cold, dark remnants drifting through space. They're no longer active players in cosmic evolution, no longer producing light or significant radiation. They simply exist, gravitational wells in space-time, patient monuments to the violent supernovae that created them billions or trillions of years earlier. The universe, once full of their brilliant pulsar signals, falls silent as the last pulsars slow below detection threshold and the last neutron stars cool into darkness. Black holes represent the ultimate endpoint of gravitational collapse, regions where space-time curvature becomes so extreme that nothing, not even light, can escape from within the event horizon. They form when the core of a very massive star, typically more than 20 solar masses, collapses during a supernova, and no known force can halt the compression. The result is a singularity, a point of theoretically infinite density, surrounded by an event horizon whose size depends on the mass involved. For stellar mass black holes, those formed from individual massive stars, the event horizon radius might be anywhere from about 10 to 100 kilometers, depending on the original star's mass. Supermassive black holes at galaxy centers, containing millions or billions of solar masses, have horizons stretching across millions or even billions of kilometers, larger than our entire solar system in extreme cases. These supermassive black holes formed through less certain mechanisms, possibly from the direct collapse of massive gas clouds in the early universe, or through the gradual accumulation and merging of smaller black holes over billions of years. Unlike white dwarfs and neutron stars, black holes don't cool in the conventional sense because they don't emit thermal radiation through normal processes. Their event horizons prevent any internal heat from escaping. However, quantum mechanics introduces a fascinating complication discovered by physicist Stephen Hawking in 1974. Hawking showed that black holes actually do radiate, very slowly, through a quantum mechanical process now called Hawking radiation. The mechanism involves virtual particle pairs that constantly pop into existence in empty space due to quantum uncertainty. Normally, these pairs annihilate almost instantly, leaving no observable effect. But near a black hole's event horizon, one particle of a pair can fall into the hole while the other escapes. From an outside observer's perspective, this appears as though the black hole is emitting particles and therefore losing mass. The radiation is thermal, with a temperature inversely proportional to the black hole's mass. For stellar mass black holes, Hawking radiation is extraordinarily weak. A black hole with the Sun's mass would have a temperature of only about 60 billionths of a Kelvin, far colder than the cosmic microwave background. It would emit Hawking radiation so slowly that it would take approximately 10 years to completely evaporate. That's 10 followed by 67 zeros, a number so large it's difficult to conceptualize. For comparison, the current age of the universe is only about 10 years, making a black hole's evaporation time trillions of trillions of trillions of trillions of times longer. Supermassive black holes last even longer. The evaporation time scales with the cube of the mass, so a black hole with 1 billion solar masses would take roughly 100 years to evaporate completely. These timescales are so vast that they dwarf every other process we've discussed. While white dwarfs cool into black dwarfs in tens of trillions of years, and while stellar remnants might decay through proton decay in 10^34 years, black holes persist for periods that make those timescales look brief by comparison. During most of their existence, black holes will be the coldest objects in the universe. As the cosmos expands and the cosmic microwave background cools toward absolute zero, black holes maintain temperatures even lower, effectively appearing as perfect absorbers that emit essentially nothing. They accumulate whatever matter or radiation happens to fall into them, slowly growing larger and colder, patient monuments to gravitational collapse that occurred trillions of years earlier. But black hole evaporation, while slow, accelerates dramatically in the final stages. As a black hole loses mass through Hawking radiation, its temperature increases because temperature is inversely proportional to mass. This creates a runaway effect. A smaller black hole radiates faster, losing mass more quickly, which makes it smaller still, which increases its temperature further, leading to even faster radiation. In the final moments of a black hole's life, it radiates intensely, potentially ending in an explosion as the last few kilograms of mass convert to radiation in a fraction of a second. These final explosions won't occur for incomprehensible lengths of time, but when they do, they'll briefly illuminate the otherwise completely dark universe. For a moment, energy will concentrate and flow, creating a brief local decrease in entropy before the radiation disperses and entropy increases overall. These will be among the last energetic events the universe experiences, the final bursts of light in an otherwise eternal darkness. Black holes also raise profound questions about information and quantum mechanics. The black hole information paradox asks what happens to information about matter that falls into a black hole. According to quantum mechanics, information cannot be destroyed. Yet, if a black hole evaporates completely through Hawking radiation, that radiation appears to be completely thermal, containing no information about what fell in. This paradox remains unresolved and represents one of the deepest puzzles in theoretical physics, potentially requiring a complete theory of quantum gravity to answer. For our journey through deep time, black holes serve as the universe's longest-lasting structures, the final holdouts against entropy and the expansion of space. Long after every star has died, every white dwarf has cooled, every neutron star has faded, black holes will remain, lonely gravitational wells in an empty, expanding cosmos, patient and cold, waiting out timescales that make the entire stelliferous era seem like a brief flash. Galaxies are not static collections of stars, but dynamic systems held together by gravity, constantly evolving through star formation, stellar death, mergers with other galaxies, and the complex interplay between dark matter, gas, and stellar populations. The Milky Way, our home galaxy, contains roughly 200 to 400 billion stars, along with vast clouds of gas and dust, stellar remnants, and a supermassive black hole at its center. But galaxies, like stars, have lifespans and fates that extend across cosmic time. Over the next few billion years, our galaxy will collide and merge with the Andromeda Galaxy, currently approaching at about 110 kilometers per second. This merger, which will begin in approximately 4 billion years and complete over the following billion or so years, will create a single massive elliptical galaxy. Individual stars rarely collide during such mergers, because the distances between stars are so vast, but the galaxy's gas clouds will compress and heat, triggering intense bursts of star formation that consume available hydrogen far more quickly than would occur otherwise. By about 100 billion years from now, most nearby galaxies will have merged into single massive elliptical galaxies, or, in some cases, been torn apart with their stars scattered into intergalactic space. The Virgo supercluster, which contains our local group of galaxies along with thousands of other galaxies, will have largely coalesced into a single gravitationally bound structure. But beyond the local supercluster, the universe's accelerating expansion will have carried other galaxy groups beyond our cosmic horizon, making them permanently unreachable and unobservable. As star formation ceases over the next 100 trillion years, galaxies transform from vibrant stellar cities into graveyards filled with cooling white dwarfs, cold neutron stars, and quiescent black holes. The last red dwarfs burn out, and no new stars replace them. Galaxies go dark, visible only through gravitational effects rather than emitted light. They become invisible collections of stellar remnants, dark matter, and the occasional lingering gas cloud, too dispersed to ever collapse into new stars. But even dark, dead galaxies don't remain stable forever. A process called dynamical friction gradually changes the distribution of stellar remnants within a galaxy. When objects of different masses orbit through a common gravitational field, they exchange energy through gravitational interactions. Massive objects tend to sink toward the center, while less massive objects get flung to larger orbits or ejected entirely. Over timescales of 10^19 to 1020 years, roughly 10 billion trillion to 100 billion trillion years, galaxies begin to evaporate. This evaporation process operates through gravitational slingshot effects. When two stellar remnants pass near each other, they exchange momentum. Sometimes this results in both objects remaining bound to the galaxy, but in different orbits. Other times, one object gains enough energy to exceed the galaxy's escape velocity and gets ejected into intergalactic space, while the other falls deeper into the galaxy's gravitational well. Over immense timescales, this process ejects roughly 90% of a galaxy's stellar mass into the void, while the remaining 10 spirals inward toward the central supermassive black hole. The remnants that fall toward the galactic center don't plunge straight in. Instead, they enter complex orbits, gradually losing energy through gravitational wave emission, an extremely weak effect for individual stellar remnants, but one that operates continuously. Eventually, over timescales comparable to black hole evaporation times, these remnants spiral close enough to the central black hole to be torn apart by tidal forces and consumed, adding their mass to the black hole's mass. Imagine the Milky Way 10-20 years from now, a period so far in the future that the current age of the universe represents only 1/10,000,000th of the time that will have passed. The galaxy as a coherent structure no longer exists. Most of its former stellar remnants drift alone through intergalactic space, scattered by billions of years of gravitational interactions. At the former galactic center floats a massive black hole, somewhat larger than it is today, containing the accumulated mass of millions of stellar remnants that spiraled inward and were consumed. This black hole is all that remains of the Milky Way's central region, a solitary gravitational well in empty space. The scattered stellar remnants, now wandering alone through the cosmos, are black dwarfs and cold neutron stars, objects at temperatures barely distinguishable from the temperature of empty space itself, which by this point has cooled to a tiny fraction of a Kelvin. They emit no light, no radiation of any kind. They're detectable only through gravitational effects, but in the vast emptiness of space, they rarely come close enough to anything else to cause noticeable gravitational perturbations. They drift, alone and patient, through a universe that has become almost entirely empty. This fate awaits every galaxy. The detailed timescales vary depending on galaxy mass and structure, but the outcome remains consistent. Galaxies are temporary structures, bound together for trillions of years, but eventually succumbing to dynamical evolution that scatters their contents and feeds their central black holes. The universe, once organized into beautiful spiral and elliptical galaxies spanning hundreds of thousands of light-years, becomes a sparse collection of isolated stellar remnants and black holes drifting through an ever-expanding void. The stelliferous era ends not with a sudden transition, but with a gradual fading and dispersal. Stars die one by one, galaxies slowly disintegrate, and structure gives way to increasing homogeneity and emptiness. By 10 to 20 years, the universe has fundamentally changed character, transforming from a cosmos of shining stars and structured galaxies into something strange, cold, and profoundly empty, setting the stage for the even longer, even stranger eras that follow. Protons, the positively charged particles found in every atomic nucleus, have been considered stable for as long as we've understood their existence. An atom of hydrogen, consisting of one proton and one electron, appears to last forever if left undisturbed. All the protons in your body, in Earth, in the Sun, were created either in the Big Bang itself or through fusion processes in stars, and they've persisted unchanged for billions of years. But theoretical physics suggests that protons might not be truly stable, that given enough time, they too will decay into lighter particles and radiation. Grand unified theories, attempts to unify the electromagnetic, weak, and strong nuclear forces into a single theoretical framework, predict that protons should occasionally decay. The process would be extraordinarily rare, with half-lives estimated at around 10 to 34 years or longer, meaning that in any given sample of protons, only an incredibly tiny fraction would decay over the current age of the universe. Experimental searches for proton decay have placed lower limits on the proton's half-life at greater than 10 to 34 years for certain decay modes, but no confirmed proton decay has ever been observed. If protons do decay with a half-life of around 10 to 34 years, the implications for the far future are profound. White dwarfs and neutron stars, composed of atomic matter held together by electromagnetic and strong nuclear forces, would gradually evaporate as their constituent protons decay into positrons, neutrinos, and gamma rays. A white dwarf, that dense sphere of carbon and oxygen nuclei supported by electron degeneracy pressure, would slowly dissolve, its atoms breaking apart one by one as protons decay. The timescale is almost incomprehensible. 10 to 34 years is 10 trillion years, a number vastly larger than the age of the universe, but still finite and calculable. If you watched a single proton with this half-life, you'd wait on average 34 years before it decayed. But white dwarfs contain approximately 10 protons, so at any given moment, roughly 10 to 23 protons per second would be decaying throughout the white dwarf, creating a faint glow of gamma rays and positrons, even though the bulk of the white dwarf's mass remains intact. As protons decay into positrons, those positrons encounter electrons and annihilate, producing additional gamma rays. The white dwarf loses mass gradually, shrinking away as its atomic structure dissolves. After roughly 10 to 40 years, several half-lives have passed, and the white dwarf has lost most of its mass. What remains is no longer a coherent object, but a diffuse cloud of electrons, positrons, neutrinos, and gamma rays slowly dispersing into space. Neutron stars face a similar fate, though the details differ. Neutrons in isolation decay with a half-life of about 10 minutes, transforming into protons, electrons, and neutrinos. But inside a neutron star, the extreme density and degeneracy pressure stabilize neutrons against decay. However, if protons can decay, then the protons that exist in a neutron star's crust, and possibly in its core, might decay according to the same timescales that apply to free protons. This would cause the neutron star to gradually lose mass and possibly destabilize, though the exact progression depends on details of nuclear physics at extreme densities that we don't fully understand. Black dwarfs, those cooled white dwarfs drifting through space in complete darkness, would also evaporate through proton decay. One moment, from a cosmic perspective, they exist as solid spheres of crystallized carbon and oxygen, diamond planets floating in empty space. Trillions of years later, they've dissolved completely, leaving behind only radiation and perhaps a few long-lived exotic particles. The universe slowly loses its matter, converting it back into energy, according to Einstein's equation E=mc2, which doesn't just govern fusion in stars, but also the decay of matter itself over unimaginable timescales. It's important to emphasize the uncertainty here. Proton decay remains unconfirmed. Experiments continue searching for any evidence that protons decay, and so far they've found none, only progressively stricter lower bounds on how long protons must last. It's possible that protons are absolutely stable, that they last forever without decay. If so, white dwarfs, black dwarfs, and neutron stars could persist indefinitely, at least until black hole evaporation consumes them or some other, even more exotic process occurs. But if proton decay does occur, even with the extraordinarily long half-lives current theories suggest, it represents a fundamental limit on the persistence of ordinary matter. Nothing made of protons can last forever. Every atom, every molecule, every structure built from chemistry and electromagnetism will eventually dissolve into radiation. The universe, which began as pure energy that condensed into matter as it cooled, would return to pure energy over timescales that make the stelliferous era seem like the blink of an eye. This process is sometimes called the degenerate era, a period when the dominant objects in the universe are degenerate stellar remnants, white dwarfs, neutron stars, and black holes, rather than actively burning stars. But if proton decay occurs, even the degenerate era is temporary, lasting only from about 1014 years to around 1040 years. After that, most matter has decayed, and the universe enters what's sometimes called the black hole era, when black holes are the only significant concentrations of mass remaining. In the far, far future, long after proton decay has dissolved most ordinary matter, a remarkable and unexpected phenomenon might occur. Black dwarfs, those cold, dark remnants of white dwarfs that have cooled to the temperature of space itself, might explode as supernova through a mechanism so slow and subtle that it operates on timescales vastly exceeding even proton decay. These explosions, called black dwarf supernova, represent perhaps the last major energetic events the universe will ever experience. The mechanism involves quantum tunneling, a purely quantum mechanical process where particles occasionally appear on the opposite side of energy barriers they classically shouldn't be able to cross. In the context of black dwarfs, quantum tunneling allows atomic nuclei to fuse even at temperatures near absolute zero, where classical physics says fusion is impossible because nuclei lack the thermal energy to overcome their electromagnetic repulsion. White dwarfs and their cooled descendants, black dwarfs, are composed primarily of carbon and oxygen nuclei, the products of helium fusion in the stars that created them. These nuclei sit in a crystalline lattice, packed tightly by electron degeneracy pressure. At finite temperatures, they vibrate in place, but at temperatures approaching absolute zero in the far future, even this vibration diminishes. Yet quantum mechanics never allows particles to be truly motionless. Zero-point energy, the minimum energy allowed by the Heisenberg uncertainty principle, keeps nuclei slightly active even at absolute zero. Occasionally, through quantum tunneling, two carbon nuclei within the black dwarf will fuse, despite having essentially no thermal energy. This fusion releases energy and creates heavier elements. The process is called pycnonuclear fusion, fusion driven by density rather than temperature. Individual fusion events occur extraordinarily rarely, perhaps one fusion event per black dwarf per trillion years. But black dwarfs are patient, and time is abundant. Over time periods estimated at around 1000 years. Yes, 10 to the power of 1100, a number so vast it's essentially meaningless in conventional terms. Pycnonuclear fusion gradually converts the carbon and oxygen in a black dwarf into heavier elements. The fusion process creeps forward, creating silicon, then iron-56, the most stable nucleus with the highest binding energy per nucleon. Iron-56 accumulates in the black dwarf's core over eons that make the current age of the universe look like a quantum fluctuation. Eventually, if the black dwarf's mass exceeds the Chandrasekhar limit of about 1.4 solar masses, enough iron-56 accumulates in the core that the electron degeneracy pressure can no longer support it. The core collapses, just as in a conventional Type Ia supernova, and the collapse rebounds as an explosion that tears the black dwarf apart, releasing energy comparable to current supernova explosions. For a brief moment, measured in seconds or minutes, the black dwarf shines as brightly as billions of suns before fading again into darkness. This black dwarf supernova would be one of the last major energetic events in the universe. By 10 to 1100 years, proton decay has long since dissolved most matter. Black holes are evaporating but haven't yet completed that process. The universe is cold, empty, and dark, expanding according to its accelerating expansion rate. And then, somewhere in that vast darkness, a black dwarf that has drifted alone for longer than we can conceptualize suddenly explodes in a brilliant flash. The energy released doesn't last. The explosion expands into space, cooling and redshifting as it spreads. Within days or weeks, the remnant cools below the temperature of the surrounding space and fades into invisibility. The universe returns to darkness, slightly more disordered than before, entropy having increased by a measurable amount. The black dwarf's constituent matter, which had existed as a coherent object since the stelliferous era trillions of years ago, is now dispersed as radiation and particles, never to recombine. Not all black dwarfs will explode. Only those with masses above the Chandrasekhar limit can accumulate enough iron-56 to trigger collapse, and many black dwarfs fall below this threshold. These lower-mass black dwarfs will simply continue existing indefinitely if proton decay doesn't occur, or will slowly evaporate through proton decay if it does. They represent a final class of stable or quasi-stable objects that might persist until black hole evaporation completes, outlasting nearly everything else in the universe. The timescale of 10 to 1100 years is so large that it defies intuitive understanding. To put it in perspective, the number of particles in the observable universe is estimated at around 10. The number of Planck times, the shortest meaningful time interval, that have elapsed since the Big Bang is around 10 to 160. The number 10^100 is larger than any quantity with physical meaning we've ever encountered, larger than the number of possible quantum states in the observable universe, larger than numbers that describe any process we can observe or measure. Yet theoretical physics allows us to calculate this time scale, to understand the mechanism, and to predict with reasonable confidence that if black dwarfs exist, and if they have sufficient mass, they will eventually explode through pycnonuclear fusion and gravitational collapse. The universe has patience that exceeds imagination, and even in nearly infinite time, rare processes can run their course, producing one final generation of stellar explosions in a cosmos that has been dark for longer than stars ever shone. After proton decay has dissolved most ordinary matter, and after the last black dwarf supernovae have faded into history, black holes become the dominant structures in the universe, the only remaining concentrations of significant mass. Everything else has either decayed into radiation, been consumed by black holes, or dispersed into the ever-expanding void. This era, sometimes called the black hole era, spans from approximately 40 years to around 100 years or longer, depending on the masses of the black holes involved. Black holes during this era exist in profound isolation. The accelerating expansion of the universe has long since carried distant galaxies beyond the cosmic horizon, making them unreachable and unobservable. Even within what was once a galaxy or galaxy cluster, the remaining black holes are separated by vast distances, measured in millions or billions of light-years, drifting through empty space with essentially no interaction with anything else. The smallest black holes evaporate first. A black hole with the mass of the Sun, about 2 × 10^30 kilograms, would evaporate through Hawking radiation in approximately 10 years. The calculation comes from the relationship between a black hole's mass and its evaporation time, which scales with the cube of the mass. Smaller black holes evaporate faster, larger ones slower, and this cubic relationship means that masses vary widely in their persistence. A black hole with 10 solar masses would last roughly 1,000 times longer than a solar mass black hole, about 10 to 70 years. A black hole with 100 solar masses would last 1,000,000 times longer still. The scaling continues upward, with evaporation times growing rapidly as mass increases. Stellar mass black holes, those formed from individual massive stars, have masses ranging from about 3 to perhaps 100 solar masses, and they evaporate over timescales from 10 to 67 to perhaps 10 to 73 years. Intermediate mass black holes, if they exist, would contain thousands to millions of solar masses and would persist much longer. But the longest-lived black holes by far are the supermassive black holes that once resided at galaxy centers. The supermassive black hole at the center of the Milky Way, Sagittarius A, contains about 4 million solar masses. Such a black hole would evaporate in approximately 10 to 87 years, an incomprehensibly long time, but still finite and calculable. The most massive supermassive black holes, those at the centers of giant elliptical galaxies or formed from the merger of multiple galaxies, can contain billions or even tens of billions of solar masses. The supermassive black hole in the galaxy M87, famously imaged by the Event Horizon Telescope, contains roughly 6.5 billion solar masses. A black hole of this mass would persist for approximately 10 to 100 years, give or take a few orders of magnitude. During most of this time, black holes emit Hawking radiation so slowly that they appear completely inert. Their temperatures are extraordinarily low, far colder than the surrounding space in the early parts of the black hole era, though eventually, as the universe expands and cools, space itself becomes colder than even the largest black holes. The radiation they emit is predominantly in the form of very low-energy photons and neutrinos, particles that carry away minuscule amounts of energy per emission event. As a black hole slowly loses mass through Hawking radiation, its properties change in subtle but measurable ways. The event horizon shrinks, contracting inward as mass decreases. The surface gravity at the horizon increases because the same mass is concentrated in a smaller volume. Most significantly, the temperature rises because temperature is inversely proportional to mass. A black hole at half its original mass has twice its original temperature and radiates 4 times faster, beginning the runaway process that characterizes the final stages of evaporation. The universe during the black hole era is almost perfectly empty and dark. Imagine the scene trillions upon trillions upon trillions of years in the future. Space has expanded enormously, stretching distances beyond recognition. The cosmic microwave background radiation, once at 2.7 Kelvin, has cooled to a tiny fraction of a Kelvin, its photons redshifted to wavelengths measured in light years. Scattered through this vast, dark expanse are black holes, solitary gravitational wells separated by distances that make interstellar distances in our era look microscopic. Nothing happens quickly. A black hole might drift for 1080 years without encountering anything, without any event occurring anywhere in its vicinity. Time passes, but with no processes running except the extraordinarily slow emission of Hawking radiation. There's little to mark that passage. The universe is, in a sense, frozen in a configuration that changes imperceptibly, waiting out the vast timescales required for black holes to evaporate. Yet change does occur. Slowly, incrementally, black holes lose mass. Photons and neutrinos stream away from their event horizons, carrying energy and reducing the black hole's mass. The process accelerates logarithmically as mass decreases, but for most of a black hole's lifetime, it proceeds at a pace too slow to describe in any meaningful human terms. A supermassive black hole might lose the equivalent of Earth's mass in 1 trillion years, a rounding error compared to its total mass. The black holes cannot last forever. Quantum mechanics, which gives rise to Hawking radiation through the uncertainty principle and virtual particle creation, guarantees that every black hole will eventually evaporate completely. The timescales are vast beyond description, but they're finite. Eventually, every black hole, no matter how massive, will radiate away its last kilogram of mass, ending in a brief flash of energetic radiation that marks the transition from the black hole era to whatever comes next. For most of a black hole's existence, Hawking radiation represents an almost negligible energy loss, a trickle of photons and particles so faint it's essentially undetectable. But as the black hole shrinks, losing mass through this slow evaporation, the process gradually accelerates. The final stages of black hole evaporation differ dramatically from the slow, patient decay that characterizes the preceding eons, transforming from subtle energy loss into violent explosion over the course of the black hole's last moments. The acceleration stems from the inverse relationship between black hole mass and temperature. When a black hole has 1 billion solar masses, its temperature is extraordinarily low, approximately 10 to 17 Kelvin, far colder than anything in the universe today. At this temperature, it radiates incredibly slowly, losing perhaps a few kilograms per year, completely negligible compared to its total mass of 2 to 39 kilograms. The evaporation proceeds at a glacial pace, but as the black hole loses mass, its temperature rises. When it's shrunk to 1 million solar masses, its temperature has increased to 10 to 14 Kelvin, and it radiates faster, though still incredibly slowly by any normal standard. When it reaches 1,000 solar masses, temperature is 11 Kelvin. At 1 solar mass, temperature is about 60 billionths of a Kelvin. The pattern continues. Every factor of 1,000 decrease in mass corresponds to a factor of 1,000 increase in temperature. Temperature determines radiation rate through the Stefan-Boltzmann law, which states that power radiated scales with the 4th power of temperature. This creates a feedback loop. As the black hole radiates and loses mass, its temperature increases, which causes it to radiate faster, which causes it to lose mass more quickly, which increases temperature further. The process feeds on itself, slowly at first, but with increasing vigor as mass decreases. For the vast majority of a black hole's lifetime, this acceleration is imperceptible. A supermassive black hole might spend 99.999% of its existence shrinking from billions of solar masses down to perhaps 1,000 solar masses, with the radiation rate remaining so low that it seems almost constant. But in the final 0.001% of its lifetime, it shrinks from 1,000 solar masses to nothing, and that final phase passes far more quickly than all the eons that preceded it. When a black hole reaches planetary mass, roughly the mass of Earth at about 6×10^24 kilograms, its temperature rises to about Kelvin, and it's emitting radiation at a rate comparable to a modest star. At this point, the black hole is shrinking noticeably, losing perhaps billions of kilograms per second. Its event horizon, now only about a centimeter in radius, contracts visibly over the course of years. As mass decreases further, the process accelerates dramatically. At mountain mass, about 1 trillion kilograms, temperature reaches 10,000 Kelvin, and the black hole glows with visible light. At building mass, 1 million kilograms, temperature exceeds 1 billion Kelvin, and the black hole radiates gamma rays intensely. The final moments approach, and the black hole transitions from patient monument to violent explosion. In the last second of its existence, a black hole might radiate with the power of billions of suns, converting its remaining mass into photons, neutrinos, and possibly other particles in a burst of energy that briefly illuminates the surrounding void. The precise details of this final explosion remain somewhat speculative because they depend on quantum gravity effects that we don't fully understand. As the black hole shrinks to Planck mass, about 22 micrograms, and Planck size about 10 to 35 meters, our current theories break down. Some theories suggest the black hole might leave behind a Planck mass remnant, a stable or quasi-stable object that doesn't evaporate further. Others suggest it evaporates completely, converting its final mass entirely into radiation, according to E-Ichthos MC2. Still others propose more exotic endings involving quantum foam, virtual particles, or other phenomena that require a complete theory of quantum gravity to describe accurately. What we can say with confidence is that the energy release in the final moments is enormous relative to the black hole's mass. When a kilogram mass black hole evaporates, it releases about 9 protons to 10^16 joules, equivalent to roughly 20 megatons of TNT, comparable to a large thermonuclear weapon. This explosion occurs in a fraction of a second, creating a brilliant flash visible across potentially millions of kilometers if anything were present to observe it. These explosions will occur scattered across the universe over immense timescales. The smallest black holes evaporate first, around 10^67 years, for solar mass black holes. Intermediate mass black holes follow at later times. Supermassive black holes evaporate last, their final explosions occurring around 10 to 100 years or later. Each explosion represents one of the last energetic events the universe will experience, brief moments of concentrated energy release in an otherwise cold, empty cosmos. The radiation from these explosions disperses into space, redshifting and cooling as it expands. Within hours or days, the energy has spread across vast volumes, diluting to the point where it becomes indistinguishable from the general background radiation of the universe, which itself has cooled to near absolute zero. The explosion's energy becomes part of the growing entropy of the cosmos, increasing disorder and approaching thermal equilibrium. After the last black hole evaporates, after the final flash of gamma rays and particle production, the universe contains no significant concentrations of mass. Everything that was once matter has either decayed through proton decay or been radiated away as Hawking radiation. The black hole era ends, and the universe enters its final, longest, strangest phase, dominated not by objects, but by diffuse radiation and quantum fluctuations in an ever-expanding void. After the last black hole evaporates, the universe transitions into what's sometimes called the photon epoch, or the dark era, a period characterized by the almost complete absence of matter and the dominance of extremely low-energy radiation. This era has no clear endpoint, stretching forward indefinitely, or at least until timescales so vast that our current physics cannot make reliable predictions. It represents the universe's final equilibrium state, as best we understand it, a cold, dark, expanding void approaching maximum entropy. The dominant constituents of the universe during this era are photons, those massless particles of light that have existed since the Big Bang, and neutrinos, nearly massless particles that interact so weakly with everything else that they effectively drift alone through space forever. Both photons and neutrinos were produced in vast quantities during the Big Bang and have been diluted by cosmic expansion ever since. But they continue to exist, redshifted to extraordinarily long wavelengths and low energies. Photons from black hole evaporation add to the existing photon background. When a black hole evaporates completely, it converts its entire mass into radiation, predominantly photons with some neutrinos and possibly other particles. A solar mass black hole produces approximately 10^57 photons during its complete evaporation, adding these to the cosmic photon bath. Across the entire observable universe, the evaporation of all black holes contributes enormously to the total photon count, though these photons quickly redshift and spread across increasingly large volumes. The universe's expansion continues unabated, driven by dark energy, if our current understanding is correct, causing space itself to stretch at an accelerating rate. This expansion redshifts photons to longer and longer wavelengths. Photons that might have been gamma rays when first emitted become X-rays, then visible light, then infrared, then radio waves, then wavelengths measured in meters, kilometers, light years, and eventually distances larger than the observable universe itself. As wavelength increases, energy decreases proportionally, since photon energy equals Planck's constant times the speed of light divided by wavelength. Temperature, defined thermodynamically as a measure of average energy per particle, approaches absolute zero. The cosmic microwave background, currently at 2.7 Kelvin, cools exponentially as the universe expands. In a trillion years, it might be a few thousandths of a Kelvin. In 10,020 years, it would be immeasurably cold, a tiny fraction of a microkelvin. In 10 to 100 years, after black holes have evaporated, temperature would be so close to absolute zero that the distinction becomes meaningless for practical purposes. Energy density also approaches zero. The universe contains a finite amount of energy distributed across an ever-increasing volume. As volume grows exponentially, due to accelerating expansion, energy density declines exponentially. Currently, the universe contains approximately 10^9 joules per cubic meter when you average across all space. In the far future, this density drops to 10^50, then 10^100, approaching zero asymptotically, but never quite reaching it unless the universe is finite in energy content. Entropy, however, continues to increase. Every process that occurs, from black hole evaporation to photon redshifting, increases the universe's total entropy. The second law of thermodynamics states that entropy never decreases in isolated systems, and the universe as a whole is the ultimate isolated system with nothing outside it. The increase slows as fewer processes occur, and as temperature approaches zero, but entropy can continue growing even in an apparently static system through subtle quantum effects. The universe during the photon epoch is unimaginably empty. If you could somehow exist as an observer, floating in space during this era, you would see nothing in any direction. No stars, no galaxies, no light of any kind, except perhaps the extraordinarily faint glow of red-shifted photons, themselves so low in energy and so widely spaced that you'd encounter one every few years at most. The darkness would be absolute, the silence complete, the emptiness total. Yet the universe is not truly empty. It contains photons, neutrinos, and possibly other stable particles like electrons and positrons, if proton decay doesn't occur. These particles exist in vast numbers, approximately 10^88 photons across the observable universe's current volume, though this number becomes meaningless as the universe expands and what's observable changes. The particles are real, possessing energy and momentum, though their energy has become infinitesimal and their density so low that they almost never interact. Theoretically, photons and neutrinos could persist indefinitely. Unlike protons, they don't decay. Unlike black holes, they don't evaporate. They simply exist, traveling through space at the speed of light for photons, or nearly the speed of light for neutrinos, red-shifting as the universe expands but never truly disappearing. In a sense, these particles represent the universe's final stable configuration, the endpoint toward which everything has been evolving since the Big Bang. But even in this seemingly static era, subtle processes might continue. Quantum mechanics allows for virtual particle creation even in empty space, the same process that produces Hawking radiation near black hole event horizons. In the vast emptiness of the far future, virtual particles occasionally become real through quantum fluctuations, producing electron-positron pairs that annihilate again almost instantly, or photons that propagate briefly before being absorbed by the vacuum. These processes are extraordinarily rare, occurring perhaps once per cubic light-year per trillion years. But given infinite time, even the rarest processes can accumulate. Some theoretical physicists have speculated about even more exotic processes occurring over timescales that dwarf black hole evaporation times. Quantum tunneling might allow vacuum decay, where the vacuum of space itself transitions to a lower energy state, potentially destroying or radically transforming the universe. Poincaré recurrence, a theorem from statistical mechanics, suggests that any finite system will eventually return arbitrarily close to its initial state, given enough time, implying that the universe might spontaneously reform galaxies, stars, or even exact copies of its current state through random quantum fluctuations. These ideas remain highly speculative and depend on physics we don't fully understand. What we can say with confidence is that the photon epoch represents the universe's approach toward thermal equilibrium, maximum entropy, and minimum available energy for doing work. It's the heat death of the universe, the final state predicted by thermodynamics, a cosmos that has run down, exhausted its gradients, and settled into eternal, cold, dark equilibrium. Even in a universe that has reached thermal equilibrium, where temperature is uniform and energy density approaches zero, quantum mechanics suggests that absolute stillness never occurs. The Heisenberg uncertainty principle, which places fundamental limits on how precisely we can know certain pairs of properties simultaneously, ensures that even empty space experiences continuous fluctuations at quantum scales. These fluctuations, normally too small and too brief to notice, might produce observable effects over the incomprehensible timescales of the far future. Virtual particles represent one manifestation of quantum fluctuations. According to quantum field theory, What we think of as empty space is actually a seething foam of virtual particle pairs, matter and antimatter particles that pop into existence, exist for timescales limited by the uncertainty principle, and then annihilate, returning their borrowed energy to the vacuum. Normally, these virtual particles never become real because they exist for such brief moments that they can't interact with anything or be observed directly. But under certain circumstances, virtual particles can become real. Near black hole event horizons, as we've discussed, one particle of a virtual pair can fall into the black hole while the other escapes, producing Hawking radiation. In the far future, in the vast emptiness of space with essentially no black holes remaining, a different process might occur. Rare quantum fluctuations, occurring with probabilities so small that they're effectively impossible over normal timescales, might occasionally create real particles from virtual ones purely through chance. The Casimir effect demonstrates that virtual particles have real, measurable consequences. When two uncharged metal plates are placed very close together in a vacuum, quantum fluctuations in the electromagnetic field between the plates differ from fluctuations outside the plates because only certain wavelengths fit between the plates. This creates a pressure difference that pushes the plates together, a force that has been measured in laboratories and matches theoretical predictions precisely. The Casimir effect shows that the vacuum is not nothing but rather a dynamic quantum system with real physical properties. At cosmic scales in the far future, quantum fluctuations might occasionally produce more dramatic effects. Statistical mechanics tells us that any configuration of particles, no matter how ordered or unlikely, has some non-zero probability of occurring through random fluctuations. This includes fluctuations that create complex structures like molecules, or even larger structures like rocks, buildings, or in principle, entire planets or galaxies. These fluctuations are extraordinarily improbable, with waiting times that vastly exceed even black hole evaporation times. But given infinite time, they might eventually occur. One particularly strange possibility is the Boltzmann brane, named after physicist Ludwig Boltzmann, who explored the statistical mechanics underlying such ideas. A Boltzmann brane is a hypothetical, self-aware entity that forms spontaneously from random fluctuations in an otherwise empty universe. The idea is that it's statistically more likely for a single brane with false memories of a larger universe to fluctuate into existence than for an entire universe with genuine history to form, given that both have non-zero probabilities. This raises philosophical paradoxes about the nature of existence and observation. If most observers in the universe are Boltzmann, brains with random false memories rather than genuine observers with real histories, then you might be a Boltzmann brain yourself, with all your memories and sense of the universe being quantum fluctuations rather than genuine experiences. Most physicists consider this unlikely and more a curiosity of statistical mechanics than a genuine prediction, but it illustrates the strange implications of infinite time combined with quantum mechanics. Poincare recurrence provides another perspective on long time-scale fluctuations. For any isolated system with finite energy, the Poincare recurrence theorem states that the system will eventually return arbitrarily close to any previous configuration, given enough time. For a finite universe, this suggests that after incomprehensibly long periods, perhaps 10,120 years, the universe might spontaneously reconfigure itself into a state similar to its current state, recreating galaxies, stars, planets, and potentially even exact duplicates of you and everyone else. The timescales involved, often called Poincare recurrence times, are so vast that they make black hole evaporation times look infinitesimal. They depend on the number of possible states the system can occupy, which for a region the size of the observable universe is approximately 10 to 10 al 120, an unimaginably large number. The recurrence timescales with this number, producing waiting periods that cannot be expressed meaningfully with conventional mathematics. These extreme timescales highlight a fundamental issue with predictions about the infinitely far future. Our physics works well for timescales we can test, from nanoseconds to billions of years. We can extrapolate with reasonable confidence to black hole evaporation at 10⁻100 years because the physics involves well-understood processes like Hawking radiation. But beyond that, uncertainties accumulate. We don't know if the cosmological constant truly remains constant. We don't know if new physics emerges at extreme scales or time scales. We don't know if quantum mechanics, thermodynamics, and general relativity continue to apply unchanged. Some theories suggest the universe might eventually undergo vacuum decay, where the vacuum of space tunnels to a lower energy state, creating a bubble of true vacuum that expands at the speed of light, potentially destroying or radically transforming everything it encounters. The probability of such decay is extraordinarily low, but over infinite time, even extraordinarily low probabilities might be realized. Other theories propose cyclic cosmologies, where universes give birth to new universes through mechanisms like black hole formation or quantum tunneling through space-time itself. The honest answer is that we don't know what happens in the truly far future, beyond 10⁻100 or 10⁻1000 years. Our physics might be complete enough to make reliable predictions, or it might be missing crucial elements that only manifest over these extreme timescales. What we can say is that quantum mechanics ensures some level of activity continues forever, that perfect stillness never occurs, and that the universe remains, in some sense, alive with possibility even when it appears dead and empty by any classical standard. The concept of heat death, formulated in the 1800s by physicists exploring thermodynamics, represents perhaps the most fundamental prediction we can make about the universe's ultimate fate. Heat death doesn't mean the universe becomes hot, but rather that it reaches thermal equilibrium, a state where temperature is uniform everywhere, where no energy gradients exist to drive processes or perform work, and where entropy, the measure of disorder and unavailable energy, reaches its maximum possible value. The second law of thermodynamics states that entropy in an isolated system always increases or stays constant, never decreases. The universe as a whole is the ultimate isolated system, with nothing outside it to exchange energy or entropy with, so its total entropy must increase over time. Every process that occurs, from stars burning hydrogen to black holes evaporating to photons redshifting, increases entropy. The universe is on a one-way journey toward maximum entropy, and that destination is heat death. Entropy can be understood in multiple ways. In thermodynamics, it measures the amount of energy unavailable for doing useful work. In statistical mechanics, it measures the number of microscopic states corresponding to a macroscopic configuration, essentially quantifying disorder or randomness. A highly ordered system like a crystal has low entropy because only a few microscopic arrangements produce that macroscopic structure. A gas has higher entropy because molecules can be arranged in countless ways while still appearing as a uniform gas. In the early universe, immediately after the Big Bang, entropy was very low despite the high temperature. The universe existed in a highly ordered state, with matter and energy distributed uniformly at extremely high density and temperature. This seems paradoxical. How can a hot, dense state have low entropy? The resolution comes from understanding that entropy depends not just on temperature, but on the number of available states. The early universe had low entropy because gravity had not yet created structure, because particles were in thermal equilibrium without significant differentiation, and because the universe's small size limited available states. As the universe expanded and cooled, gravity began pulling matter together into stars, galaxies, and larger structures. This seems to create order, decreasing entropy, which would violate the second law. But the detailed accounting shows that while local entropy decreases when stars form or galaxies coalesce, the total entropy increases because these processes release tremendous amounts of heat and radiation that spread throughout space with high entropy. The entropy decrease in forming a star is vastly outweighed by the entropy increase in the radiation it produces. The formation and evolution of stars represents a particularly efficient entropy generation process. A star converts low-entropy hydrogen into higher-entropy helium and heavier elements while radiating enormous amounts of photons that carry away even more entropy. The Sun, during its lifetime, will increase the universe's entropy by approximately 10 to the 57 joules per Kelvin, a number almost too large to comprehend through fusion and radiation. Multiply this by hundreds of billions of trillions of stars across cosmic history, and the entropy production becomes astronomical. Black holes represent the universe's most efficient entropy generators. A black hole's entropy is proportional to the area of its event horizon, not its volume, and this entropy is enormous. A solar mass black hole has entropy of about 10^54 joules per Kelvin. A supermassive black hole with 1 billion solar masses has entropy of about 10 joules per Kelvin. When black holes evaporate through Hawking radiation, they convert this enormous entropy into radiation dispersed across space, further increasing total entropy. The heat death scenario envisions the universe reaching a state where all available energy has been converted into forms that cannot perform work. All matter has either decayed into radiation or been consumed by black holes that have subsequently evaporated. All energy exists as photons and neutrinos redshifted to arbitrarily low energies, distributed uniformly across space. Temperature is uniform everywhere at a value arbitrarily close to absolute zero. No gradients exist, no differences in temperature or density or any other property that could drive a process. In this state, entropy has reached its maximum value consistent with the universe's total energy and volume. No further processes can increase entropy because all configurations are equally probable, all states equally accessible. The universe has achieved thermal equilibrium, and thermodynamics tells us that systems at equilibrium don't spontaneously evolve away from equilibrium without external intervention. Heat death represents a final state, stable and unchanging apart from quantum fluctuations that average to zero over time. This doesn't mean the universe is destroyed or ceases to exist. The photons and neutrinos still exist, still possess energy and momentum, still travel through space. Quantum fields still pervade all of space. Space-time itself continues to exist and expand. But nothing happens anymore in any meaningful sense. No complexity, no structure, no processes that require energy flow. The universe exists in a state sometimes called maximum entropy or heat death, cold, dark, and unchanging forever. The arrow of time, that sense of past being different from future, might dissolve in such a state. The arrow of time arises from entropy increase, from the fact that systems evolve from low entropy states to high entropy states, creating a directionality to temporal evolution. When entropy reaches its maximum and stops increasing, when all states are equally probable, the arrow of time disappears. Past and future become indistinguishable because nothing distinguishes them. No process is running that could define a direction. Some find this vision of the universe's fate profoundly depressing, suggesting that everything we do is ultimately meaningless because the universe will end in cold, dark emptiness regardless. Others find it liberating or simply interesting, a natural consequence of physical laws that have no obligation to align with human preferences or hopes. The universe is what it is, and understanding its trajectory doesn't diminish the meaning or value we find in our brief moment within it. While heat death through eternal expansion represents our current best understanding of the universe's fate, alternative scenarios remain possible depending on the nature of dark energy and the universe's total density. These alternatives include the Big Rip, where accelerating expansion tears space-time itself apart, the Big Crunch, where expansion reverses and the universe collapses back to a hot, dense state, and various cyclic models where universes repeat in endless cycles. The Big Rip scenario occurs if dark energy strengthens over time rather than remaining constant. Current observations suggest dark energy behaves like a cosmological constant, maintaining constant density even as the universe expands. But some theoretical models propose phantom energy, a form of dark energy that increases in density or strength over time, causing the universe's expansion to accelerate ever faster. If phantom energy exists, the acceleration eventually becomes so extreme that it overcomes all other forces, even those binding matter together at atomic scales. The scenario unfolds in stages. First, galaxy clusters tear apart as the expansion rate between them exceeds their mutual gravitational attraction, occurring perhaps 200 billion years from now in extreme phantom energy models. Then individual galaxies tear apart as expansion overcomes the gravity holding them together, maybe 60 million years before the final rip. Closer to the end, perhaps 3 months before the rip, individual solar systems disintegrate as expansion tears planets from their orbits around stars. 30 minutes before, stars and planets themselves rip apart, their gravity unable to resist the exponentially accelerating expansion. In the final moment, atoms disintegrate as electromagnetic forces can no longer hold electrons in orbit around nuclei. Finally, atomic nuclei themselves tear apart and potentially space-time itself fragments into disconnected pieces. The universe ends in a violent destruction where everything, down to the fundamental fabric of space, is torn apart by runaway expansion. Current observations don't support the Big Rip scenario. Measurements of dark energy's equation of state, the ratio of its pressure to density, suggest it behaves very close to a cosmological constant with ut equals 1, where W represents the equation of state parameter. Phantom energy requires WW, 1, and current data constrain W to be very close to, making phantom energy unlikely though not completely ruled out. Future observations might detect subtle evolution in dark energy that would change this assessment. The Big Crunch represents the opposite scenario, where the universe's expansion eventually stops and reverses. This requires either that dark energy eventually weakens or disappears, or that the universe contains enough matter for gravity to overcome the expansion. Current observations suggest neither condition holds. The universe appears to have insufficient matter density to halt expansion, containing only about 30% of the critical density needed if dark energy didn't exist, and dark energy shows no signs of weakening. In a Big Crunch scenario, expansion slows, stops, and reverses sometime in the future, perhaps trillions of years from now, if it happens at all. Galaxies that were receding begin approaching. The cosmic microwave background, which has been cooling due to expansion, starts heating up again as radiation blue shifts instead of red shifting. Eventually, galaxies collide, stars merge, and temperature rises to levels not seen since shortly after the Big Bang. As the crunch continues, matter collapses into denser and denser configurations. Stars vaporize then ionize as temperatures exceed millions of degrees. Eventually, nuclei themselves break apart into protons and neutrons, then into quarks. The universe compresses back toward a singularity, potentially ending in conditions similar to the Big Bang, but in reverse, a final convergence of all matter and energy into infinite density and temperature. Some theories propose that the Big Crunch might not be an ending, but a transition, that the universe might bounce, undergoing a cyclic pattern of expansion and contraction repeating eternally. In these cyclic or oscillating universe models, each crunch leads to a new bang, creating a new expansion phase, which eventually crunches again, continuing forever. Each cycle might be identical or might differ in laws of physics, constants of nature, or initial conditions, creating an infinite sequence of universes. These cyclic models face significant theoretical challenges. Entropy increase seems to violate cyclicity, because each cycle would have higher entropy than the last, suggesting either the cycles grow longer and larger each time until they approach infinite duration and size, or some mechanism reduces entropy during the bounce, violating the second law of thermodynamics. No satisfactory resolution to this problem has been found, though various proposals involving quantum gravity effects or higher dimensional physics have been suggested. Another alternative involves false vacuum decay. Current physics suggests we might live in a metastable vacuum state, similar to supercooled water that's liquid below freezing, because crystallization hasn't nucleated yet. The true vacuum might have lower energy, and quantum tunneling might eventually create a bubble of true vacuum that expands at light speed, converting everything it encounters to the lower energy state. Depending on the properties of true vacuum, this could destroy the universe as we know it, or merely transform it into something unrecognizable. The timescale for vacuum decay is completely unknown, potentially infinite if the current vacuum is truly stable, or finite but vastly longer than the current age of the universe if it's metastable. We have no way to predict when or if such decay might occur. It could happen tomorrow, though the probability is infinitesimally small, or it might never happen at all. Some physicists argue that if vacuum decay were likely on timescales less than the age of the universe, it probably would have happened already somewhere in the observable universe, and the fact that we exist suggests either the vacuum is stable or the decay timescale vastly exceeds the current age of the cosmos. Our current best understanding, based on observations of cosmic expansion, measurements of dark energy, and theoretical considerations, suggests eternal expansion leading to heat death as the most probable fate. The universe will continue expanding, driven by dark energy, cooling and diluting forever, approaching but never quite reaching absolute zero and infinite size. This represents not a dramatic ending, but a gentle fading, the universe running down like a clock whose spring gradually unwinds until motion becomes imperceptibly slow, but never completely stops. Looking forward across timescales measured in 10 to the 1,000 years, a number so vast it essentially means unimaginably far in the future, requires letting go of intuitive understanding and embracing pure mathematical extrapolation. At these timescales, every process we've discussed, from star death to proton decay to black hole evaporation, has long since completed. What remains? What processes might continue? What does existence even mean across such vast temporal expanses? The number 10,000 defies easy comprehension. It's 10 raised to the power 1,000, which equals 1 followed by 1,000 zeros. To put this in perspective, the number of atoms in the observable universe is estimated at roughly 10 to the 80. The number of Planck volumes, smallest meaningful units of space, in the observable universe is approximately 10 The number of possible quantum states in the observable universe might be around 10^10^120, which is 10 to the power of 10 to the power 120, an even more incomprehensibly large number. Yet 10,000, while large, is still vastly smaller than 10^120 and represents a timescale we can at least write down and manipulate mathematically, even if we can't truly grasp its magnitude. At 10,000 years, if proton decay occurs with timescales around 10,034 years, all ordinary matter has long since decayed into radiation. White dwarfs, black dwarfs, neutron stars, even exotic forms of matter have dissolved, their constituent protons decaying into positrons, neutrinos, and gamma rays that have since redshifted into oblivion. If proton decay doesn't occur, these objects might persist, though black hole evaporation would have consumed many of them anyway through gravitational interactions over the intervening eons. Black holes have also completely evaporated by this point, even the largest supermassive black holes that persisted for 10,100 years before finally radiating away their last particles. Their evaporation releases photons and neutrinos that join the vast sea of radiation filling the expanding universe. The universe contains no concentrated masses, no structures, nothing but extremely dilute, extremely low-energy radiation spread across volumes beyond description. The cosmic microwave background, which started at about 3000 Kelvin shortly after the Big Bang and has cooled to 2.7 Kelvin today, has cooled to temperatures approaching absolute zero so closely that the difference is meaningless. If the universe has expanded by a factor of roughly 10 or more since today, which seems plausible given accelerating expansion over 10,000 years, the background temperature would be around 10 Kelvin or lower, indistinguishable from absolute zero for practical purposes. Yet quantum mechanics tells us that even at temperatures arbitrarily close to absolute zero, quantum fluctuations continue. The vacuum energy, that baseline energy density of empty space, persists. Virtual particles still pop in and out of existence according to Heisenberg uncertainty. Zero-point energy, the minimum energy required by quantum mechanics, remains non-zero. The universe never becomes truly static, never completely runs down to a state of absolute nothing and perfect stillness. Over these timescales, processes that seem impossibly rare become possible through sheer temporal abundance. Iron nuclei, if they still exist from the pre-proton decay era, or if protons are stable and iron has formed through other processes, might undergo quantum tunneling fusion, pycnonuclear reactions that occur without heat through pure quantum probability. As mentioned earlier, the timescale for significant pycnonuclear fusion in black dwarfs is estimated around 10,000 years, so at 10,000 years, this process has barely begun. But it illustrates how patient the universe can be, how willing to wait for even the most improbable events. Quantum tunneling might also allow other exotic processes. Protons, if they haven't decayed, might tunnel into neutrons, plus positrons, plus neutrinos, even if they're absolutely stable against normal decay, given enough time for the tunneling probability to be realized. Entire atomic nuclei might tunnel through barrier penetration into different isotopes or elements. Electrons might tunnel between atoms separated by astronomical distances. None of these processes occur on human timescales, or even on timescales comparable to stellar evolution, but given 10,000 years, they become possible. Poincaré recurrence becomes relevant at these timescales. The Poincaré recurrence theorem states that a finite system will return arbitrarily close to any previous state, given enough time. The recurrence time depends on the system's phase space volume, essentially the number of possible configurations. For a region the size of the current observable universe, This gives recurrence times around 10⁻120 years, vastly longer than 10⁻1000 years, so recurrence hasn't happened yet even at this extreme future time. But subsections of the universe might experience local recurrences. A small region of space containing perhaps a few cubic light-years might have a phase space small enough that recurrence occurs on timescales of only 10,000 years or so. In such regions, random quantum fluctuations might spontaneously create structures, perhaps simple molecules or even complex ones, not through any deterministic process but through sheer statistical mechanics over vast time. These fluctuation-created structures would be extraordinarily rare and brief. A molecule forming through random fluctuations would quickly fall apart again through subsequent fluctuations, existing for perhaps microseconds before dissolving back into the quantum foam. Creating anything complex or stable through fluctuations requires exponentially more time as complexity increases, so even at 10⁻1000 years, only the simplest possible structures might appear occasionally through this mechanism. Some theoretical models suggest space-time itself might be unstable over these timescales. Virtual black holes, quantum fluctuations in the fabric of space-time that create tiny black holes lasting for Planck times before evaporating, might occasionally coalesce through some exotic process into larger structures. Or quantum tunneling might create pockets of different vacuum energy, baby universes that pinch off from our space-time and expand into separate, disconnected cosmoses, unreachable and undetectable from our own. The expansion of space continues relentlessly if dark energy persists. At 10⁻1000 years, the universe has expanded by factors that dwarf current scales. Regions that are currently separated by billions of light-years would be separated by distances measured in numbers with thousands of digits, so vast that light emitted from one could never reach the other, even given infinite time, because space between them expands faster than light can traverse it. The observable universe from any given point shrinks toward zero as everything races away beyond the cosmic horizon. In such a universe, causality becomes almost meaningless. Events in one region cannot influence events in distant regions because no signal can propagate between them faster than light, and space expands too quickly for light to ever bridge the gap. Each tiny patch of space becomes its own isolated universe, cut off from all others, evolving independently according to local quantum fluctuations and whatever sparse radiation or matter it happens to contain. Despite all this, the universe exists. Space-time persists, even if almost entirely empty. Quantum fields pervade all space, even if their excitations are rare and fleeting. The laws of physics continue to operate, governing the behavior of particles and fields, even when almost nothing is happening. The universe has not ended, not been destroyed, but has transformed into something utterly different from what we experience now, a cosmos of incredible emptiness, coldness and stillness punctuated only by occasional quantum events that flash into existence and vanish again almost instantly. And so we arrive at the end of our journey through deep time, having witnessed the death of the last star, the evaporation of the final black hole, and the approach toward maximum entropy across timescales that dwarf human history the way human history dwarfs the lifespan of a mayfly. We've contemplated a future so distant that our current epoch, with its brilliant stars and dynamic galaxies, seems like a brief spark in an eternal night. Yet in understanding this distant darkness, we gain profound insight into the light we experience now. You exist in what cosmologists call the stelliferous era, a golden age of cosmic history when stars dominate the universe's visible matter-energy content, and when complexity, structure, and the energy gradients necessary for life are abundant. This era began roughly 100 million years after the Big Bang, when the first stars ignited, and it will continue for perhaps 100 trillion years until the last stars fade. On a timeline stretching from the Big Bang to the heat death of the universe, the stelliferous era occupies less than 1% of cosmic history, a brief flourishing sandwiched between primordial darkness and eternal night. The privilege of existing during this era cannot be overstated. The energy flowing from stars provides the gradients that allow for complexity. Fusion in stellar cores creates heavy elements necessary for rocky planets, complex chemistry, and life as we know it. The radiation from stars warms planetary surfaces, drives atmospheric circulation, and provides energy for photosynthesis and other life-sustaining processes. Without stars, none of this would be possible. But more fundamentally, the fact that we exist at all during this era, rather than in the far future, reveals something about the nature of observers and complexity. Complex structures like galaxies, stars, planets, and living organisms can only form and persist during periods of high energy flow and low entropy relative to maximum. The far future universe, approaching maximum entropy, cannot support such complexity. Any observers capable of contemplating the universe must necessarily exist during eras like our own, when entropy is still increasing and energy gradients still exist. This anthropic reasoning, the observation that our existence constrains what we can observe about the universe, doesn't explain why the universe has these properties, but it explains why we find ourselves in this particular epoch. We couldn't exist in the far future universe any more than fish could exist in a universe without water. Our existence during the stelliferous era is not coincidence, but necessity. A selection effect where observers can only arise during periods when the universe permits observers to exist. Understanding the universe's far future also illuminates the nature of time and change. Time, as we experience it, has a direction, an arrow pointing from past to future, from low entropy to high entropy, from order to disorder. This arrow of time governs our lives, our memories, our sense of causality and progression. But in the far future, as entropy approaches maximum and change ceases, the arrow blurs and potentially disappears. Time might continue in some abstract sense, but without processes to mark its passage, without change to distinguish one moment from the next, time loses the meaning we currently ascribe to it. The heat-death scenario reveals that the universe is fundamentally temporary in its current form. Nothing lasts forever. Not stars, not galaxies, not even protons, if current theories are correct. Everything transforms, following the inexorable laws of thermodynamics toward states of higher entropy and lower available energy. This impermanence, this inevitable evolution toward equilibrium, is not a flaw or tragedy, but simply how the universe operates, the natural consequence of physical laws that have remained consistent since the Big Bang. Some might find this knowledge depressing, a cosmic nihilism suggesting that all human endeavor is ultimately meaningless because the universe will end in cold darkness regardless of what we do. But this perspective mistakes temporal duration for significance. The meaning we find in our lives, the love we share, the knowledge we gain, the beauty we create and appreciate, these are not diminished by their temporal limits. A sunset is not less beautiful because it fades into night. A song is not less moving because it eventually ends. Human life is not less valuable because it's brief compared to cosmic timescales. Indeed, one could argue that impermanence creates value precisely because it's scarce. If stars shone forever, their light would be taken for granted. If complexity and structure were eternal and unchanging, they would lose their preciousness. The fact that the stelliferous era is temporary, that we live during a special time in cosmic history when the universe blazes with the light of hundreds of billions of trillions of stars, makes this era more remarkable, not less. The journey through deep time also emphasizes the extraordinary success of human understanding. Using mathematics, observation, and theoretical physics, we can make reliable predictions about events that will occur trillions of years in the future, timescales beyond direct verification, yet accessible to human reason. We understand the life cycle of stars from birth to death. We can calculate black hole evaporation times using quantum mechanics and general relativity. We can project the expansion of the universe into the far future using cosmological observations and thermodynamics. This predictive power represents one of humanity's greatest achievements. We are mortal, living for mere decades, inhabitants of a small planet orbiting an ordinary star in an unremarkable galaxy. Yet through careful thought and observation, we've unraveled cosmic mysteries spanning billions of light years and billions of years, understanding processes that occurred before Earth existed and will occur long after it's gone. The universe is knowable, and we have proven ourselves capable of knowing it. As we conclude this journey, let the knowledge of cosmic timescales settle gently into your awareness. The stars above you tonight are temporary, burning through their fuel at rates we can calculate precisely, destined to fade in futures we can predict. The galaxy that holds those stars will eventually disperse or merge, its structure eroding over timescales measured in trillions of years. Even the black holes, seemingly permanent features of the universe, will evaporate given enough time. But you are here now, in the golden age, when stars still shine, when galaxies still spiral, when energy gradients allow for complexity and life. You are made of stardust, atoms forged in stellar furnaces and supernova explosions, assembled through billions of years of cosmic evolution into a form capable of understanding that very evolution. You are the universe contemplating itself, matter organized in such a way that it becomes conscious and wonders about its origins and fate. The darkness ahead, incomprehensible as it is, serves to illuminate the present. Knowing that stars will die makes their current shining more precious. Understanding that complexity is temporary makes current complexity more wonderful. Recognizing that we exist during a special time in cosmic history creates gratitude for this particular moment, this particular configuration of matter and energy that allows for galaxies, stars, planets, and minds capable of appreciating them. So rest now, knowing that you've journeyed across cosmic time, witnessed futures beyond imagination, and returned to the present with deeper understanding. The stars will continue burning for trillions of years yet, providing light and warmth and the heavy elements necessary for life. The universe has time, so much time, and you exist in its golden age, privileged to witness beauty that won't last forever, but lasts long enough for countless generations to experience wonder. Let your breathing slow, your thoughts quiet, your consciousness drift toward rest. The universe expands around you, patient and vast, following laws that govern the smallest particles and the largest structures with equal precision. Those laws have carried the cosmos from the Big Bang through 13.8 billion years of evolution to this moment, and they'll carry it forward through futures we can imagine but never witness, futures where stars fade, where darkness returns, where entropy reaches maximum and change ceases. But that's tomorrow, cosmically speaking. Tonight, the stars still shine. The galaxy spirals. Life persists and wonders and dreams. Sleep peacefully, knowing your place in cosmic history, knowing the preciousness of this moment, knowing that understanding the darkness helps us appreciate the light. Dream deeply, rest well, and when you wake, the stars will still be there, burning patiently through their fuel, providing light in the cosmic night. The universe is patient. The universe is vast. And you, for this brief moment in cosmic time, are part of its story. Conscious matter contemplating existence, light appreciating light, the cosmos knowing itself through you. Sleep peacefully. Dream deeply. Remember gently. The stars shine on.